Hello, we are starting with section 3 of chapter 3 of the linear algebra book that we are using. And this is where matrices make a comeback. Remember, towards the beginning of the course, we introduced matrices as some kind of data container, simply a container of numbers, of coefficients from linear systems. And in this way, we didn't have to write many variables and very many plus and minus signs when dealing with, when solving linear systems. Instead, we applied the row operations from Gaussian elimination simply on matrices that are made up of coefficients of the linear systems. So that reduced our clerical work. We also already established some facts about matrices, in particular row rank equals column rank, which allowed us to define simply the rank of a matrix. And we also used matrices for examples of vector spaces. For example, M2 by 2, which was the set of all 2 by 2 matrices, is an example of a vector space. But now we are coming to the main use of matrices, which is to represent linear maps. Let me start by reminding you that a linear map is determined by its action on a basis. So if we know what a linear map H does to some basis vectors, then we know everything about the linear map, because take an arbitrary vector from the domain space V, represented as a linear combination of the basis like this. Then, because linear maps preserve linear combinations, we have this equality here, which gives us a linear combination of the h of beta I. So if we know these h of beta I, we know the whole map. And this is what we called extending a map linearly from a basis to the whole vector space. And now I'm going to show you an example which basically shows you almost everything I'm going to show you in this video, so pay good attention. It's a pretty generic example, so not too special, but also not too complicated. So let's say we have a domain space V, I will also call it input space today, and a codomain space W, R2, I will also call this an output space. And we have corresponding bases, again not too simple, not too complicated, for the input space and the output space, and I might call these bases input bases and output bases. I hope this is all intuitive. Now we fix some random linear map, and as I just explained, we can do so by simply fixing its action on the input basis. So 1 here is also beta 1, and 1 plus x is beta 2 on the next slide, and 1 plus x squared is beta 3. So if we fix what h does on these beta I, we have fixed the whole of h, as I've just explained. Okay, and now once we have fixed these results, we express these vectors with respect to the output basis. So we write, for example, this vector 0, 1 as a linear combination of the basis elements from the output basis. When we do this, we get these two coefficients. And then if we collect these coefficients in a column vector, we get what we call the representation of h of beta 1 with respect to the output basis. And we do the same thing for all three h of beta I. Now we get 3 column vectors, 3 times 2 numbers. And we put these 3 column vectors in a matrix as column vectors. So you see they appear as columns of this matrix. And this matrix is what we are going to call the matrix representation of H with respect to the given bases. In particular, note that this matrix doesn't talk about any specific input to H. We've only characterized H itself, and we could do so by simply saying what H does to the basis vectors. And now if we go to an arbitrary vector from the input basis V, we may of course, as I explained earlier, express it in terms of a linear combination of the input basis. And then by linearity we get this equality. Now this h of beta I we've just expressed in terms of the output basis. And if we now multiply this out and regroup, we get this expression, which gives us h of v as a linear combination of the two vectors from the output basis. So what we've actually computed here is a representation of h of v with respect to the output basis. See that we've collected the coefficients from this linear combination in the two entries of this column vector. Now what have we done so far? So on the one hand, we have computed a matrix which corresponds to H, and on the other hand, we've represented an arbitrary input vector V with respect to the input basis, like here. And now it looks like that by combining this matrix and this vector in a relatively simple way, we can obtain the representation of h of v with respect to the output basis. You should observe that these numbers that appear in the matrix here appear now as coefficients in this vector. And if we take a closer look, you see that in fact we obtain the top entry of this vector by taking a dot product of the first row of this matrix with this vector, and similarly by taking the dot product of the bottom row of the matrix with this vector C1, C2, C3, we get the bottom entry of this result vector. Let's put this in some general form by using letters. So let's suppose that V and W are vector spaces of dimensions n and m with bases b and d respectively, and then h of V of W is a linear map. So now we take the basis vectors, the beta I, send them through H, and compute the representation of h of beta I with respect to the output basis. Now the output space has dimension m, so the entries of these vectors, well, there will be m entries, and we put these m tall vectors in a matrix, which we call like this, representation with respect to b and d of the map H. So that's the matrix representation of H with respect to b and d. These subscripts here and here sometimes help to clarify things, but we may also omit them. Okay, so again, this only characterizes the map. It doesn't speak about any specific input yet. Let's look at a few examples. Let's say we consider projection onto the x-axis. That is the map that simply makes the second component 0 and leaves the first component untouched. And let's again fix a fairly unspectacular basis. in fact, two bases for R2, two different ones, so that you get sort of the general picture. And then we apply the same program. So we take the two input basis vectors, apply them to our linear map, now called pi. And then the result of applying pi to the basis elements, well, the results are 1, 0 and minus 1, 0. And we represent them with respect to the output basis. So for example, if we represent 1, 0 with respect to the output basis, we get this vector. Let's check this. So hopefully 1, 0 would be minus 1 times the first vector from the output basis plus a half times the second vector from the output basis. And in the top component we have 1, what we want, and in the bottom component we have 0. Good, so that's correct, and probably that is also correct. Now we have represented pi of beta 1 and pi of beta 2 with respect to the output basis. We take these two column vectors, put them in a matrix like this, which gives us a representation of pi with respect to B and D. Now let's take the same map but a different basis, and then hopefully we'll not be surprised that we obtain a different matrix. Let's now simply take the standard basis, E2. Then what does pi do to the vectors from the standard basis? Well, it does this, what I'm circling here. Now the representation of these two vectors with respect to the standard basis are the vectors themselves, because we have chosen the standard basis. And you see how the matrix is obtained. Let's look at yet another linear map from R2 to R. Let's again just use the standard basis. 1, 0 maps to 2, 0, 1 maps to 3. Now we represent 2 and 3 with respect to the standard basis E1. And we get that, well, this is this 1 tall vector 2 and the 1 tall vector 3. And by putting these numbers in a matrix, we get this 1 by 2 matrix representation of H with respect to the standard bases. And now here's the theorem that we have observed already in the initial example. So if we have the same assumptions as before, and we represent H with respect to basis B and D, and now we take an arbitrary input vector V and represent it with respect to the input basis, then we can combine the matrix with this vector to get a representation of H of V with respect to the output basis. And again, you obtain this vector by taking a dot product of the first row with this vector. That gives us the first entry, and you get the second entry by taking a dot product of the second row with the vector, etc. So the proof is really just doing the initial example with more letters to obtain full generality. Now I hope it makes a lot of sense to define the matrix vector product of a matrix and a vector. It is defined so that this vector here becomes the product of this matrix with this vector. So we define a matrix vector product so that we have precisely this connection. And this is simply what I've already explained. So you take the dot product of the first row with the column vector to get the first entry, and then you do the same thing for the second entry. You might easily have seen such a definition before, maybe at school. It's unlikely that you have thought very much about linear maps. And you might as well define a matrix vector product just without talking about linear maps. You can just simply take some numbers and then practice taking a matrix vector product. The product is not well defined if the number of columns of the matrix is not equal to the number of entries of the vectors. So it's only defined if the number of columns of the matrix, here n, is equal to the height of the vector. So this is not defined. Well, now we apply the theorem to the examples that we have seen. We have previously represented this projection map with respect to some bases B and D, which gave us this matrix representation of the map. Now we take some kind of arbitrary domain vector V, represented with respect to the input basis, which gives us this vector, as you can verify here. So the coefficients from the expression of V with respect to the input basis are these two numbers, 2 and 3. And now in order to get a representation of the image of V under pi with respect to the output basis, we can simply multiply this matrix with this vector. So that vector here, 1 minus 1 over 2, is a representation of pi of V with respect to the output basis D. Here's the numerical verification. Let's go to that example again. From R2 to R, we have already computed the representation of this map with respect to the standard basis. Now take some random domain vector V represented with respect to the standard basis. So that's in this example the vector itself, as is always the case when we deal with the standard basis. And now in order to get the representation of h of v with respect to the standard basis, we multiply the matrix that we've obtained earlier with this vector to get 2. So, and that is a representation with respect to the standard basis E1 of the vector space of real numbers. So that means h of v is 2. Of course, you can verify this easily. 2 times minus 2 is minus 4, plus 3 times 2, 6. So minus 4 plus 6 is plus 2.